Okay, well, it's a real pleasure to be here. As Lars said, please feel free to interrupt, and if I only get through the first 10% of the talk, that's just fine. So I'm going to talk about mapping the dark cosmos. So what does that mean? Well, what you can see on my title slide is actually the part on the left-hand side is the dark part of the universe that we cannot actually measure directly, because it doesn't emit or absorb any light. The part on the right-hand side is the galaxies that we can actually see with large telescopes. And so we want to measure these galaxies in order to learn about that dark stuff that we can't see. And one of the reasons that we want to measure that dark stuff is because we want to learn about sort of this middle thing, which is supposed to represent kind of the fundamental constituents of the universe. What is it made of? And that's one of the big questions that I'm really interested in. So, yes?
On the chart,
yes,
there were three colors.
Yes.
There was one you talked about, the other, the little sliver. You didn't say.
Yeah.
What's that?
Yeah. So actually, the little sliver is you and me and all of the galaxies and all of the gas in the universe.
Wow.
Everything on the periodic table and everything in the standard model of particle physics is in that little sliver.
So what are the other two parts?
I'm going to talk about that in just a minute. Just a minute.
I question the slide on the left. You said that's the dark part. We can't see it, but there's a bunch of veiny-looking stuff.
Yeah.
What's that? If I can't see it, I can see it.
Yeah. So that was actually a simulation. So I made that part up in my computer. And now we're going to try to measure what it's actually doing, and I'll try to explain that piece. Okay, so what is driving this research? Really big questions, like how did the universe begin? What is it made of? What is the geometry of the universe on very large scales? And how does all of the stuff in the universe form? And most of the stuff in the universe is in galaxies. And so that's sort of the unit that I think in. So we can get a little bit more specific. And I first actually came to the KITP almost 20 years ago as a graduate student. And at that time, sort of the version of these questions was like this. So we had an idea, a good theoretical idea for how the universe might have begun, or how it might have spent its first tiny fraction of a second. Okay? And that idea is that the universe in its first tiny fraction of a second expands extremely fast. So fast that it actually expands faster than the speed of light. And in that first moment creates all of the matter in the universe, and also creates all of the fluctuations in the matter distribution. So that was a really compelling idea that explained some basic facts that we knew about the universe at that time, but there was really little direct evidence. We had this question, what is the universe made of? We already knew at that time that most of the mass in the universe was not stuff that emits or absorbs light, but we really didn't know even these basic things like to an order of magnitude, how much matter is there and what kind of matter is it? Okay. We had this question about what is the geometry of the universe, and in cosmology, the geometry is related to the ultimate fate of the universe. So this is related to questions like, will it expand forever? Will it stop expanding and recollapse? Or, just continuously slow down? And we have this question about galaxy formation. What provides the seeds of structure formation? How do those things grow and become what we see today? So how can we learn more about this? Well, what I'm basically going to be talking to you about today is mapping the sky, and what we can infer from the maps we make of the sky. And I'm going to start with the maps we make of the very, very early universe. Okay, so that's mapping the sky very far away. And when I say very far away, I'm now talking about basically 13.8 billion light years away. Okay, and so this is a map that we have made of the baby universe. This is something that we call the cosmic microwave background. Okay, what is this? This is a map of temperature fluctuations in the early universe about 380,000 years after the Big Bang. And those temperature fluctuations, we've actually kind of blown them up in this plot. They're actually really tiny fluctuations at this time. They're about 1 part in 100,000 at this time. And those were created during this process that we call inflation. At least that's our current theory, and it seems to be supported by all of the evidence. So the amazing thing about these temperature fluctuations, those correspond to density fluctuations. So the places where the universe is a little bit hotter or cooler at this time correspond to places where the universe was a little bit more dense or a little bit less dense. And you can see in this plot on the upper left how much our measurements of those fluctuations have improved since the very first measurement was made with the COBE satellite in 1992. You can see it was a very fuzzy map. We got a little bit more precise in 2003 with the WMAP satellite, and now with the Planck satellite. These are all satellites in space that are essentially making measurements. Just what they're really measuring is just the temperature of the cold universe. It's about 2.73 degrees above absolute zero. And yeah.
What are those ripples?
Yeah, I'm going to get to that in just a second. Okay, so this is the actual map that we make, and on the right-hand side, I'm showing this line is just essentially characterizing how big these wiggles are on different scales. Okay, so this is telling you about how big these wiggles are on large scales, and this is telling you about how big these wiggles are on small scales. Okay, so you can actually see that the biggest peak here, it turns out that this number down here, don't worry about what the actual number is, that corresponds to something on the sky that it's about 1 degree. So that's actually the biggest spot size that you see in this map. And it turns out that all of the features in this thing that just looks like a bunch of wiggles, they have specific physical meaning. So we actually know how to take this line and turn it into a theoretical model about what the universe is made of. It's quite amazing. So there actually is a line underneath these data points. So these are real data points. These are all measurements that have been made by these satellites and similar satellites. Actually, some of them are on the ground. These ones over here are mostly from the ground. These ones over here mostly from space. So there is a line underneath those points, and that line is a model which is described by just 6 parameters. Those 6 parameters essentially describe things about what the universe is made of. I'll say more about those parameters in just a minute. Okay, but the basic idea that we have this incredibly precise picture of what the universe looked like at this very early time, and we know how to map those measurements directly into a simple theoretical model about what the universe is made of. And this is the amazing and somewhat shocking model that we have come to in the last 20 years. And even though this model is kind of strange, it's in some ways really beautiful, and it really describes almost all of the measurements that we have made, not just of the cosmic microwave background, but also of the late-time universe, as I'll be talking about later. So in this model, what is this model? So here's that same pie chart I showed you before. Now I've actually labeled it. So in this model, we have the idea that there was this first tiny fraction of a second in the very early universe that created all of the matter and also created those fluctuations in the matter. We think we understand gravity. We think it's described just by general relativity, and that seems to hold on every scale that we've measured so far, both from scale of the solar system all the way out to the scale of the whole universe. We think that the mass in the universe is dominated by something we call dark matter. We're not quite sure what that dark matter is, but we know that it doesn't interact in the same way as normal matter does with electromagnetism. So it interacts exactly the same way with gravity, as far as we know, but not the same way with electromagnetism. It just basically doesn't emit or absorb light. Yeah?
Why the difference between 26% on
Yeah.
the chart and 85% up there?
Yeah, so what I've done here, just to confuse you with fractions, is, so dark matter is 85% of the matter. So if I only look at the red part, it's 85%. If I look at the whole pie, light, it's about 26%. Yeah.
One question. Most of the particles in the standard model don't react with light, aren't they? Wouldn't that be dark matter?
Actually, they do mostly interact with electromagnetism. Yeah.
A lot of them weren't supposed to. I guess I'm not an expert in it. I just had a layman's course.
Yeah. So all of those.
So most of the particles in the standard model do in fact react in some way.
Just in normal way with electromagnetism. So that's all. That's pretty much everything over here.
I guess we wouldn't
in this
count it if
5%.
they didn't, right?
That's right.
Okay.
That's right.
Risa?
Yeah.
One question. So it's really dark matter. Is that a gravity balancer? Because it would be, the universe would be expanding faster if you didn't have dark matter with the gravity.
Right. So we can infer its presence from lots of different scales, all the way from individual galaxies to the whole universe, and I'll be saying a little bit more about that. But yeah, that's right. Okay, and then we have this other strange piece of the puzzle, which here I've labeled dark energy, and here I've called it cosmological constant. I'll say more about this, but cosmological constant is the simplest idea of what it might be. It's the idea that there is some sort of property of space. Space itself has some energy density, and whatever that is doing, it is making the universe expand faster and faster with time. So the expansion rate is actually accelerating.
Accelerates, yeah.
It's actually accelerating. Okay, and we also think we know that the geometry of the universe is flat, so that does not mean that it looks like a pancake. It means that like the geometry you learned in high school, Euclidean geometry, it still works on the scale of the whole universe. So if you draw a really, really big triangle, like as big as the whole universe, its angles still add up to 180 degrees. Okay? Yeah.
Does everyone believe that?
Yeah, this part, yes. So I'll actually show you a number, I think. But yeah, so this is now measured to be true at I think the 0.1% level. Yeah.
How do you measure something like that?
Yeah. So actually, it turns out that was one of the numbers that went into this model. So all of those things actually went into drawing this line. And actually, the position of this peak right here tells you about the geometry of the universe. Amazing. But if the universe was like, you can think of something not flat as like being on the surface of a sphere or like a saddle or something, and that would shift the position of this peak. Okay, so the amazing thing is that line that I just showed you and all of those spots in the previous plot, that can basically be described by 7 numbers. Okay, 7 numbers. 4 of them describe the amounts of different kinds of stuff. So how much normal matter, the stuff that you and me and the sun and most of our galaxy is made of. How much dark matter, how much dark energy, or how much of it is in this cosmological constant, and how much neutrinos. Neutrinos is a very small fraction, but it's not 0. We've actually measured that it's not 0. We're trying to understand exactly what number that is. Then there's a number which describes the current expansion rate of the universe, right? We want to know how fast is the universe expanding. And then there's essentially 2 numbers that describe the sizes of those spots. Like the overall normalization of the spots, how clumpy is it? And then, is it more clumpy on large scales or more clumpy on small scales? That's what this number is. Okay? So those are all, numbers that you can think about. And the amazing thing is when I was saying 20 years ago, we didn't know what these numbers were. Many of them sometimes by a factor of 10. And now these are the kind of measurements that we have of these numbers. So you can see that they're very small error bars, and we also know the age extremely precisely. So it really is 13.8 billion years. It's not 13.7. It's not 13.9. It's a kind of amazing. Yeah.
I've always thought of the universe on a 3-dimensional model. What is the meaning of the term "the universe is flat"?
Yeah, so it is 3-dimensional. Flat it's a way to describe the geometry. So if it were 2-dimensional, then it would look like a plane instead of like a surface of a sphere or a saddle. Yeah. But it's not 2-dimensional. It's 3-dimensional, and that just describes this fact that I told you about the very large triangle, or like 2 parallel lines. If you draw 2 parallel lines in the universe, they will never cross. But if it was...
Is it like a big pancake then?
No. It may be infinite, and it is three-dimensional. It's not a pancake. I don't mean it's squished. I just mean that that's how the geometry works.
I'll take your word for it.
You're going to have to.
Despite all the excellent precision you have here, you still have this inflation going on in the beginning.
Mm-hmm.
Is there a sense that we will ever understand that, or is that just the Mr. Fix-It?
No, I think it's actually, I think one of the most amazing things is I really think it's not just a Mr. Fix-It. I think almost the most incredible thing about this story in the last 20 years is that we don't quite have direct evidence for inflation, but there were lots of other ideas for what could be doing that. Those have all been ruled out. There basically is no other really good idea, as far as I'm concerned. And that doesn't mean it's right. I mean, somebody might come up with a better idea tomorrow. That's always the case in science, right? But the idea of inflation actually makes very specific predictions. One of the interesting predictions that it made was that this number, NS, which was totally unknown when I went to graduate school, totally unknown, it made a prediction that this number would be close to 1, but a little bit less than 1. And there's a very specific reason that it does that. But you can see that prediction turned out to be true. So I think that's actually quite incredible. Okay, so despite all of this, there's still so many puzzles that this is not good enough. Physicists are kind of impatient, so we still want to learn more. And so let's try. So far, I just told you about mapping the sky, the very early universe. Now I'm going to talk to you about mapping the sky a little bit more nearby. Yeah.
Why couldn't you go back before 380,000?
Yeah, that's a great question. I didn't really tell you much about the physics of what creates that map. So the reason 380,000 years is a special time is because the universe was very hot and very dense in the beginning. Mostly what's been happening is it's just been expanding and cooling, okay? And a magic thing happened at that moment. The universe got cool enough that you were able to form atoms. So before that time, the electrons could not stick to their nuclei. And so the photons that were running around kept running into electrons, and it just nothing, it was like a big crowded room. They couldn't get anywhere.
Like a shield.
Yeah.
Is that when the universe became transparent?
Effectively, yeah. There is another time that sometimes people talk about transparency called reionization, but yeah. So basically what happened since that time is that the photons from that time just were able to just free stream to us. And mostly they have just come in a straight line to us from that time. Turns out it's not quite a straight line because there's stuff in the way.
Is that related to temperature and gravity? Why that moment at 380?
That moment because before that moment, the universe was so hot that electrons couldn't stick to their nuclei. Yeah. Okay, so I now want to talk about mapping the sky nearby. So this is just a very local map. This happens to be one that's all sky, so it's pretty. You can see the Milky Way there. And these points here are actually individual galaxies. So every dot in this map is an individual galaxy that's been mapped out in the sky. And because I'm a cosmologist, this seems all really nearby to me. It's a little strange. Okay, so every single one of these is a galaxy. You can see already in this map interesting things. You can see that it's not smooth. It's pretty clustered, right? And remember I told you that CMB map, that map I showed you already was clustered at just 1 part in 100,000. Somehow we get from that very smooth map to this very, very clumpy map, okay? And so a lot of what I do is try to understand, how do we get from here to here? That's a lot of what I do. And the basic point is that those numbers that I told you already, that 7-parameter model, that was just from this map. Okay? And so if I can actually make predictions for how this happens and then measure this whole process, I can get a lot more information. Okay? I can really get a lot more information about the last 13.8 billion years and also about these fundamental questions in physics. What is the universe made of? Okay, so I first want to talk about, what do we expect to measure? So the nice thing about the universe is that on large scales, gravity dominates. So all of the other forces are unimportant in the universe on large scales. And that's nice because gravity is actually pretty easy. So what do we do in order to understand what happens in the last 13.8 billion years? Well, we take this map, basically tells us the initial conditions of our problem. That is, connected to this question of what the universe is made of. We turn on gravity. That's an apple from a descendant of Newton's tree. And it turns out that we actually have to use a really big computer. We have to use a big computer because this problem very rapidly becomes nonlinear. So we can't just do it with pen and paper. So we have to do fairly complicated calculations. And this is an example of one of those kinds of calculations. So this is a cosmological simulation of just a large arbitrary region of the universe. And in this particular simulation, you can see, actually, often when you see these movies, the dark matter is colored. In this one, we've actually colored the dark matter dark. And the bright spots are just the dense regions of the universe, and that's where we expect to get galaxies, actually. So this is the kind of simulation that we do in my group, and it allows us to make predictions for where all of the matter is and also where all of the galaxies are. Okay.
The light matter seems to be where the dark matter is.
It is, yeah. I'll say more about that.
Oh, there must be a reason.
Yeah.
That was
I'll say more about that.
Does the question of which came first, the galaxy or the black hole, come into these calculations?
Yeah. So mostly the black holes are just happening at the very centers of galaxies. So they happen after the galaxies start forming. They do impact the later stages of galaxy formation. But
you've concluded the black hole came first.
No, I've concluded that the stars came first and in a tiny galaxy, and eventually that galaxy got bigger and formed black holes. Yeah.
You talked about there being evidence for dark matter on scales from individual galaxies up to the scale of the whole universe. What about on the solar system scale? Really, it doesn't influence the...
Yeah, so in our very local neighborhood, there is some dark matter. I mean, I think there's probably about 1,000 dark matter particles going through my thumbnail every second. But it's actually not dominating the dynamics. So within the solar system, actually, we can explain most of what happens just by looking at the normal stuff.
Given the pie chart here, why wouldn't the solar system be dominated 5-1 by dark matter?
Yeah, so I'm going to answer your question in a few minutes. Okay. So that picture I showed you actually depends on what the universe is made of. So it depends on that pie chart. Okay. So how do we figure this out? So there's two main ways I'm going to talk about that we study the contents of the entire universe. Okay. So the first thing we can do is we can measure how fast the universe is expanding. Okay. So now let's just think this through. So if we have more mass, whatever kind of mass it is, if we have more mass, that mass pulls things together. More mass, more gravity, so it'll pull things together. And so that's actually going to slow down the expansion rate. Okay? Now we have this other thing, which I mentioned to you, this strange thing called dark energy. We don't really know what it is, but oops, maybe it's some sort of repulsive energy of empty space. And the consequence is that empty space pushes other empty space apart. Okay? So we can measure the expansion rate again. What will dark energy do? Well, more dark energy will push things apart. So it actually will speed the expansion up. Okay? And so these things kind of counteract. They don't counteract perfectly, but they act in opposite sign, with opposite sign. Yeah?
When you say it pushes things apart, do you mean it twists space-time in some way, or do you mean it, in the ordinary sense, moves objects away?
Yeah, so that is actually quite important. It's not twisting space-time, but it is stretching space. What it's really doing is stretching space. Yeah. Okay, so that's the first way, measuring the expansion rate. The next way is measuring how fast structure grows. Yeah.
Before you go off that, dark energy is pushing matter apart. Is dark energy part of your cosmological constant?
Yeah. So cosmological constant is the simplest case of dark energy. So we don't know for sure that it's constant, and that's why I'm using this more general term of dark energy. The simplest case, which is currently consistent with all of the data we have, is that it is a constant property of space. It's the same throughout all space and time. It's just a constant property of space. That I call a cosmological constant. That's a special case. It's the simplest case of dark energy. It might be more complicated. It could change with time or over space or something.
Sorry, I had one more question.
Yep.
So you've got dark matter, which is tending to hold things in place. And you have dark energy, which is pushing them apart. You have to make assumptions about both. So if you assume there's less dark matter, that means there's also less dark energy. So how do you figure that out?
No. So yeah. So I'm gonna, if I don't answer your question in the next 10 minutes, you ping me again. Okay. Okay. So next thing that we can do, separate from measuring the expansion rate, is we can measure how fast structure grows. What do I mean by structure? I mean, individual galaxies, but also how galaxies are clustered together on large scales. Okay, so like in that movie, you saw that there was structure actually on a wide range of scales. So what will more mass do? Well, more mass, just like it did before, it pulls things together, right? And so it makes things clumpier. It makes things get clumpy faster, right? So the more matter you have, the faster your universe will get clumpy. Okay, you can do this again with dark energy, and you can ask, what does dark energy do? Well, more dark energy, it pushes things apart, or it stretches space, like we said. And so that will mean that it's essentially counteracting the gravity that's pulling them together. Okay? Okay, so what have we learned about this so far? Yeah?
Sorry. If dark energy is stretching space, it can presumably do that faster than the speed of light. But if you look at the other half of the question, doesn't that get limited to the speed of light?
Yeah, so that's right. So gravity cannot happen at faster than the speed of light. But you're right that in principle, dark energy could be expanding, stretching space faster than the speed of light. We actually think that happened. Something like that happened during this inflation process. The actual rate of the expansion right now is way, 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 way slower than that. So it's nowhere close.
But what that means, surely, is that there is no arithmetic relationship between
that's
the
right.
one and the other.
That's definitely true, and I'll be saying more about that. Yeah. So that was a simplification just to give you a sense of the sign, but they're not totally interchangeable, which is nice because that means we can learn more. Okay? Okay, so what have we learned so far? So I told you already that the universe is accelerating. Here are just two pieces of evidence that we have for those. These are two totally different measurements, totally different kinds of measurements with different kinds of objects. And they're both telling us the same thing. So some of you might have heard of this thing called supernovae. And this was the original famous discovery in 1997 that actually got the Nobel Prize for discovering the accelerating universe. And, this is an interesting story that they actually were trying to measure. So the basic idea is these things are what we call standard candles. It's like you have a 60-watt light bulb, and you just put it at different distances, and then you measure how bright that object is, how bright it looks, and then that tells you about how bright it actually is. It tells you about how the universe is expanding. And so with those measurements of supernovae, we find, so there's 3 lines here corresponding to these 3 models, and you can see that only one of them fits. It's the one that has roughly 70% in a cosmological constant, and 30% in matter. This is a totally independent measurement called Baryon acoustic oscillations. I'm not going to explain that term right now, but I'll explain it later. What I'm going to explain right now is that just like this is a standard candle, you can think of this as a standard ruler. So what does that mean? It means I have some physical scale where I know the actual physical scale. Like just like this, I have like, you know, a 3-meter ruler, and now I'm going to put it at different distances, and I'm going to see how big the ruler looks. And that's basically what I'm doing here, and that allows me to measure the expansion rate of the universe. Okay? And this is now measuring the expansion rate actually going back almost 10 billion years. You can see it's still not a very precise measurement back in time, but you can already see that the universe was slowing down. That's what you have. If you have a universe that's made only of matter, you have a universe slowing down. And then something strange happened here, that the universe started speeding up. That was when dark energy started to become dominant. Okay? So what is doing this accelerating? Well, you know, I don't know. Nobody knows. It's really one of the biggest questions in all of physics. So we already talked about this a little bit. The simplest idea is this idea of a cosmological constant that would be the same throughout all space and time. It could be something that's some sort of field that changes with time and maybe even with space. It could be that on the largest scales, general relativity is wrong. And so we need to get a new theory of gravity. And so we're really trying to understand this. But what we do know, we know a few things about this. We know what it's doing to the expansion rate today. That's well measured. We know what it tells us about the geometry. So basically, we know that that pie chart has to add up to this magic number 1. You know, that's roughly what we know. But we have lots of different lines of evidence for this. So somebody asked me already about what are these different kinds of measurements telling you. And what you can see here is that there's 3 colors on this plot. This axis is how much matter you have, and this axis is how much of the universe is in the cosmological constant. And what you can see is that these 3 measure different combinations. So this is what the supernova measure. They measure this combination of these parameters. This line is what the cosmic microwave background measures, and this line is what that standard ruler measures. And they're all kind of lining up around the same spot. Yeah.
We call it the cosmological constant, meaning it's constant throughout the whole universe. Well, that implies that maybe the universe is in dark matter rather than the dark matter is in the universe. If it was in the universe, then it should be smaller as it gets farther away. And if the universe is in the dark matter, then it would in fact be a constant.
Okay, I didn't follow that, but what I will say is already I think you've confused dark matter and dark energy.
Well, all right. Well, that's fine.
Okay. Yeah. Okay. So dark matter is normal matter. So as the universe, expands, matter dilutes.
I probably meant to say energy.
Maybe.
You know.
As the universe expands, matter dilutes, right? So as the universe expands, you actually have less and less dark matter per unit volume. You have more space, same amount of stuff. But the energy doesn't.
So maybe we're floating in the dark energy, and it's not confined to our universe.
Yeah, maybe. I don't know.
That's the multiverse approach, you know, really.
Well, that's different than the multiverse.
All these multiverses are floating in the dark energy.
Maybe. Okay, so the next thing to say is that all of our current results are consistent with this cosmological constant idea. And this consistency is actually already quite impressive. So what I'm showing in this plot, so remember I told you about two kinds of ways we can measure the universe, the expansion history and the growth of structure. And what I'm showing in this plot, don't worry about the axis, except for that this is time, this is today, this is looking back in time, this is about 7 billion years ago. What I'm doing is these gray lines, these are predictions that just come from that very first map I showed you of the very early universe. This is the prediction from that map of what the growth of structure and the expansion rate would be doing. And now I can go and measure what it is actually doing. And I find that it's totally consistent with my prediction which was 13.7 billion years in the past. So this is quite an amazing prediction from this theory, right? So there's 6 numbers that go into there. I measure those 6 numbers 13.8 billion years ago, and I use them to make a prediction about what happened over the last 7 billion years. Okay? But actually, one thing you'll notice from this plot is that right now, the error bars are actually larger than the size of the prediction. So we would like to make these error bars a lot smaller. We want to test this model at much, much higher precision. Okay? And that's what I'm going to talk about for the rest of the talk. Okay. But before I talk about that, I just want to sort of reassess this question about the big questions, right? Where are we today, right? Compared to how I described these questions as we thought of them 20 years ago. So I think we really are at the stage where we can measure details of the physics of inflation. It's quite amazing. We actually are able to, through the kinds of measurements that I'm telling you about, measure things about what was happening in the first tiny fraction of a second, because they actually impact the fluctuations and how they evolve. In this question of what the universe is made of, I still don't know what the dark matter is, but I really have I know almost exactly how much there is, and I can really ask more detailed questions. Do the predictions from sort of our most popular idea of dark matter really match in detail when I look at the galaxy distribution? I can ask, what are the masses of the neutrinos, and can I see their impact on how structure forms? I know now the geometry of the universe, and I know it's accelerating, and now I want to understand what's doing that, right? So is it a new energy component, or is it just a cosmological constant, or does it change with time, or is it a modification of gravity? And then I'm also interested in all of the other stuff in the universe, in particular, how do galaxies form? How is galaxy formation driven by and embedded in the formation of structure? And how does the physics of galaxy formation actually impact that structure? Okay, so how can we learn more than we did already? So I'm going to talk more about this path here. And I'm going to talk about this new generation of both imaging and spectroscopic surveys that's starting to map the universe basically over the last 10 billion years or so at much, much higher precision than we have so far. And we really want to ask this simple picture, simple but confusing and quite bizarre picture that I told you, does it still hold together at the next level of precision, or is there some new physics that I haven't understood? And one of the messages that I want to give you is that the sort of ultimate power of these surveys that I'm going to tell you about really depends on how well we can understand how galaxies form within the evolution of the distribution of matter. And that's actually the main thing that I've been here at the KITP studying for the last 11 weeks or so. Okay, so here's another movie similar to the one we saw before. And this movie is only different in that what I'm doing is I'm going to just show you some of the things that we look for specifically when we look at these movies. In this one, the dark matter is white. Sorry, I changed the color scheme just to confuse you. And what you can see here is that I'm circling the peaks in the dark matter distribution. And these are just 2 plots of the sort that cosmologists make. When we do a movie like this, we want to count, how many things are there. This is just number as a function of the mass of the thing. So you can see the big things got colored red over here, and they got colored red over here. Okay? So I can make predictions like this as a function of the parameters in my cosmological model. Okay? Now, what those plots actually look like depends on how much stuff there is in my universe and what the nature of dark matter is. So that's the really cool thing. Now I'm going to make I'm doing 2 different movies. This is an example of 2 movies which looked almost the same 13.8 billion years ago. They had basically the same fluctuations at that time, but they had different values of the fluctuations today. So part of that pie chart was a little bit different, or some of those 6 numbers were a little bit different, and so they ended up looking quite a bit different.
How do you predict that?
So the only thing that goes into these movies are those initial fluctuations. Basically, what did that wiggle plot look like that I showed you in the very beginning? And gravity. That's it. Okay? So anyways, you can see that if these are the kind of predictions, and now I can go out and try to measure these things. in the late-time universe. Okay? So one of the things that you noticed in these movies is that you can see these clumpy regions, which started out just being kind of fuzzy. Some of them collapsed, and it's like a tug of war in these collapsed regions between gravity and expansion. So you have expansion pulling everything apart, gravity pulling everything together. But in some regions where you had initially a little bit more stuff, gravity wins in the end. Okay? And when that gravity wins, those things essentially decouple from the expansion. They become gravitationally bound. And we call those things dark matter halos. And those dark matter halos are where we think we form every single galaxy. Every single galaxy we think forms actually at the center of a dark matter halo. So what happens here is that you start out with the gas and the dark matter just well mixed. They're just smoothly distributed in the same way. And once you get a collapsed region, there's a key difference between galaxies and dark matter. The normal stuff is mostly at that time made of hydrogen gas. And the key difference between hydrogen gas and dark matter is that when gas particles hit each other, they cool down. They lose a little bit of energy when they run into each other. And because they lose a little bit of energy, they start moving slower. And so they actually sink to the center of these dark matter halos. That doesn't happen with the dark matter because they don't experience electromagnetism. You can think of it as they basically have no friction. So they hit each other, nothing happens. Gas particles hit each other, they cool down, they sink to the center, they start to make stars, and that's where we get galaxies. So we actually can measure this. We can measure this by looking at the dynamics of galaxies. We can measure this in galaxy clusters by looking at the dynamics of galaxies moving inside those clusters. And we can also measure it on the scale of the whole universe. Okay? So I go back to this plot. This is just a plot of the distribution of dark matter in the nearby universe. And so galaxies form by gravity in the regions that have the most dark matter. They only form where there's a lot of dark matter. So you said earlier it looks like the galaxies are in the same place as the dark matter. They are almost in the same place. They only form where there's a lot of dark matter. So sometimes you can have some dark matter and no galaxies. You never have a galaxy and no dark matter, as far as we know. Okay? So we can predict where these galaxies form in this model universe. And this is my one-slide summary of my last 11 weeks. So this is the title of the program I've been running here at KITP. We're looking at the connection between galaxies and dark matter halos. And the really simple thing that we've learned is that more massive galaxies live in more massive halos. That's not very strange. That seems like makes sense. You know, you have a lot of dark matter. You also get a lot of gas. But if you talk about the fraction of the mass of the dark matter that actually turns into stars, it's not a constant function. So actually it peaks roughly right around the mass of the Milky Way. The Milky Way is sort of a typical galaxy. And the Milky Way is the massive object where you are most efficient at turning your gas into stars. Turns out there's a lot of physics that happens both at the high mass end and at the low mass end. At the high mass end, actually, somebody asked about black holes. At the high mass end, you can have galaxies have black holes in them. Those black holes can eject some energy into the gas, and they can heat it up and stop it from cooling and forming more stars. And so that reduces this. And on this side, the galaxies are really fragile. So you've got little tiny galaxies in dark matter, and they start to form stars. And they have supernovae, and those supernovae can blow out all the gas and also prevent future star formation. So there's a lot of complexities here, but this is sort of the simple picture. And so with this very simple picture, I can take this picture of dark matter and I can turn it into a picture of galaxies. How the galaxies are distributed. Okay, here's how, so you can see that those look really similar, but not identical, right? There were places where I had a little bit of dark matter and it was not enough to get a galaxy, right? Okay, so this is a prediction that I can actually make of how the galaxies are in my universe, and now I can go out and measure that. Okay, so what can we measure? Well, we can measure lots of things about this. We can measure, you know, the places where there's a lot of galaxies. We can measure the places where there's no galaxies. We can measure, you know, if I have a galaxy here, am I more likely to get a galaxy over here or less likely than random. So those are the kinds of things that I can measure. All of these things are a function of those 6 numbers. Right? They are a function of those cosmological parameters. And so they can tell us, if I measure this map really precisely, they can tell us about what dark energy is, what dark matter is. They can even tell us about the physics of inflation and the mass of the neutrino, because those things actually have an impact on the galaxy distribution, which is quite amazing. So here's a simple version. This is a model that actually half of this movie are observations of galaxies in the Sloan Digital Sky Survey, where we've actually mapped out the positions of galaxies. This was sort of the survey that happened over the last 10 or 15 years. The other half of this movie is a model that I made in my computer, where I put in those 6 numbers, I asked how dark matter evolved, I populated that with galaxies, and then I did a bunch of statistics and showed that they basically looked the same. The places where it's dark are just places where the telescope didn't point yet. They're not actually empty. Okay, so you could see, if you squint, you probably can't tell the difference between the right side and the left side. Okay, but we can now go ahead and measure this at much higher precision. So that's what I'm going to talk about now. So now I'm going to talk about kind of the future of what we're doing with this stuff. Okay, so there's a lot of words on this slide. I don't want you to worry about the details, but want you to come away with the idea that we're doing these 2 kinds of surveys. One kind of survey, we're basically taking pictures. Okay, we're just basically taking pictures in multiple bands with big cameras of as much sky as we can and mapping out galaxies in over as much of the universe as I can. And I wrote here 2 plus D. So a picture is just a 2D picture. It's a little bit more than 2 dimensions because we can get some information about the distance, but it's pretty fuzzy information. So it's kind of like just medium quality resolution in the 3rd dimension. And then we can do 3D mapping. We do that by actually measuring a spectrum for every single galaxy, and that spectrum tells us about how fast the galaxies are moving away from us, and that really gives us almost a 3D map. Okay? And for both of these kinds of surveys, we can make different kinds of measurements. Okay, so remember that I told you before that there's 2 basic kinds of things we're going to measure. We're going to measure expansion, and we're going to measure the growth of structure. So the cool thing here is with these 2 kinds of surveys, with pictures and with spectra, we have lots of ways to measure things that give us different combinations of expansion and growth of structure. So different ways of basically making that map and measuring aspects of that map tell us different pieces of this, okay? And so that gives us a lot of consistency checks to really understand, do all of the pieces of this puzzle fit together when we measure it at high precision. So I'm going to talk specifically about 3 surveys, 2 imaging surveys, the dark energy survey, which is happening now, LSST, which will happen in about 5 years, and DESI, which is a spectroscopic survey that will start happening in a few years. Okay, so DES is an imaging survey. We're looking at about 1/8 of the sky. We'll be able to map out 300 million galaxies.
Oh my word.
And that's actually, I started working on this survey when I was a postdoc. I wrote the very, very first proposal for this survey in 2004. It took a while to get started, but we finally got it going. Built a new camera. Dark energy spectroscopic instrument. We're going to be measuring spectra for 35 million galaxies. These are a lot more expensive per object than images. So you can see that the numbers are smaller. And then the LSST, which is a really exciting imaging survey, really the biggest project happening in astronomy. And I'll say more about all of these surveys. Okay, so the dark energy survey. This is a telescope in Chile. It's a new camera that we built for this existing telescope. 5-year survey. It's about 1/8 of the sky. And as I said, 300 million galaxies. So the exciting thing that we're doing right now, many of us working on this survey have been here at the KITP doing this analysis. We're actually doing this cosmology analysis for the first year of data. Actually, we already have the 4th year of data in hand. This shows you how hard this analysis is, basically. But that first year so it'll be about 1/5 of the total data. It's a little less than 1/3 of the total area. And we're working on that now. So as I said, it's basically different ways of measuring the expansion history and the growth of structure with different kinds of measurements. So we do measurements of supernovae. We do measurements. One of the most interesting things is a measurement called weak gravitational lensing. So those 300 million or maybe 200 million galaxies that we measure, we get really what we want to do is we want to measure their shapes really precisely. And why is that interesting? Well, what general relativity tells you is that every time a photon travels through space, if there's mass in the way, the photon will bend a little bit. That mass will bend in space, and then the photon will travel around that mass. And so that happens, you might have seen dramatic pictures of that happening in really dense regions of the universe, but literally every single photon, those ones that I told you have been traveling to us all the way from the CMB, every single one of them is getting a tiny, tiny bit bent from all of the matter along the line of sight. And that tiny bit of bending actually changes the shapes of galaxies. So it's a very precise measurement that we're making. It's a tiny effect, but we luckily have 200 million objects to measure it on. So this is a hard measurement. We need really big collaboration. So DES has about 400 scientists from all over the world. It's great. We get to go to these places when we have our collaboration meetings. So it's been, yeah.
Does microlensing change the shape of the galaxy or change the shape of how we see it here on Earth?
Yeah, so this is actually not microlensing, but that's okay. This is weak lensing, which is a different regime than microlensing. But right, so it changes the way it doesn't actually change the shape of the galaxy. It changes the way the light comes to us and the way we see it in our telescopes. Okay, so this is one of the most interesting things we can do with this survey is actually, as I said, make a map. So this is a map of the galaxies, just measuring every galaxy and plotting the points. Which is very, very exciting. You're some of the first people to see this map. This is a map, 1,500 square degrees, of the mass in this piece of the universe. Okay, so this is measured through this weak gravitational lensing. So these places where you see red spots, that's where you have a lot of extra stuff along the line of sight. So this is a projection. So we're actually kind of integrating over the last 7 billion years. And these blue spots are where you have very underdense regions along those lines of sight. And so we can actually learn a ton from this map. It's quite cool. I want to take a 1-minute diversion and tell you about one of the other really exciting things we've done with the Dark Energy Survey. This has been this amazing renaissance in the discovery of tiny little galaxies that are orbiting our own Milky Way. So we call these guys dwarf galaxies. You might have heard of 2 galaxies that orbit the Milky Way. If any of you have been to the southern hemisphere, there's 2 you can see, the Large Magellanic Cloud and the Small Magellanic Cloud. In the southern sky, you can look up and see those objects in the sky, but those are the 2 largest ones. It turns out we now know of 52 of them. 52 galaxies that orbit, 54, I guess, sorry, that orbit our own Milky Way. And half of those were discovered just in the last couple of years. And the reason they were discovered is that this is what those galaxies look like. So this is actually a random piece of sky, except for it's not quite random. To eye, it looks like almost random. But if you actually make a color filter and you only look for objects that are sort of in a specific color range, then you get this. This is the galaxy. This is a dwarf galaxy that one of the ones that we discovered using these imaging data. So you really need this very regular imaging data, and this is the part of the sky that DES looked at. These were things that were discovered previously with the Sloan Digital Sky Survey. That survey was not as deep, but it looked at more of the sky. So it was able to find things more nearby. You can see these are the ones that were discovered by Sloan, and then DES turned on and we discovered all these other ones. So we expect that there's at least 100 more of these yet to be found. Okay, so you guys are some of the very first to see this plot. This is a preliminary result from the Dark Energy Survey, but there's something kind of weird about this plot. Don't take the numbers seriously. I know you don't even know what they are, so that's fine. You're a good audience for this. So we do, these measurements are so precise that what we do is we try to make sure we don't bias ourselves when we do these measurements. So we blind all of our results. So these error bars are shifted, these contours are shifted by some arbitrary amount that nobody in the collaboration knows until we're absolutely sure that we've done our analysis right and we've checked all of the things we can possibly think of to check. So the exciting thing about this plot is that these blue lines, those are the measurements of these two parameters. I'll tell you what those parameters are in a second. This one is the thing that's going to tell you about whether we have a cosmological constant or something else. And this parameter is the thing that basically tells you how clumpy are the spots overall. Okay? So these blue lines are the measurements from the cosmic microwave background, and these red lines are the measurements from the dark energy survey. Now, you should not believe that they're on top of each other. That's arbitrary. I've just put them on top of each other because I don't know the answer yet. Okay? But these papers will come out in the next month or so. The main exciting thing is that we actually have similar precision between these two totally independent measurements. So we're getting to the place where we can measure the local universe almost as well as we could measure those simple spots that I showed you in my first slide. So this is really the first time that's been true. And this is just with 20% of the data, so we still have a ways to go. Okay, I know I'm running out of time, but I want to just say a few words about these other measurements. So the dark energy spectroscopic instrument is also a new instrument. It's being built for the twin of the Blanco. So these are twin telescopes. One's in Chile, one's in Arizona. We built an imaging camera for one and a spectrograph for this one. And as I said, we'll be measuring 35 million galaxy and quasar spectra. So to give you a sense of what that means, right now we have about 3.5 million total that anyone has ever measured with any instrument. So this is about an order of magnitude more than that. And also probing about an order of magnitude more in volume. And so what we're really trying to do is cover as much volume as we can. So we basically are getting the 35 million easiest redshifts you can measure. But we're probing a huge amount of volume. So this is one third of the sky. And we're going back essentially 10 or 11 billion years. Making this 3D map. And to give you a sense of how much of an improvement it is, this is what our current galaxy map looks like at a given redshift. Okay, these are the galaxies that we've measured, and this is what this will look like when we do this with DESI, and this is just in the nearby universe. These spots are just stars. These are stars in the way, and so you can't measure all the galaxies behind them. Okay, I think I'm running out of time, so I'm not going to be able to tell you in detail about what this baryon acoustic oscillation thing is, but this is the main motivation for DESI. So I'll just say really briefly, those spots in the cosmic microwave background, right, those were caused by these fluctuations at that time, essentially this fluid of photons and baryons that was oscillating at that time. And the reason you saw those wiggles was because there was actually oscillations in that fluid. Those oscillations in the fluid, the exact same physics, can actually be seen today in the galaxy distribution. And that's what we're measuring with the baryon acoustic oscillations. So it's a beautiful measurement because it's really simple physics that we really think we understand. As I said, we think it's a standard ruler. We know the physical scale of basically how big those fluctuations should be. And so we can measure that physical scale on the sky and measure its angular size. And that gives us a measurement of the expansion history. So that's what this will look like. I showed you this plot before. These are our current measurements. This is what DESI will be able to do. So these are not real data yet, but if the universe was as simple as we currently expect, this is what it will do. And you can see it's a beautifully precise measurement. This is the expansion history, but the other amazing thing about DESI is it also, at the same time, measures the growth of structure with the same 35 million galaxies. So that's a different kind of measurement you can make with the same objects. So what really happens is that in these dense regions, things get a little bit squished because things that are moving towards or away from you look a little bit different along the line of sight than they do along the sky. And what that gives you is a measurement of the growth rate. And so we should be able to distinguish something like a cosmological constant from weird kinds of gravity models that would look the same in the expansion history, but different in the growth of structure. And that's because general relativity, there's a direct connection between these two. So if you measure one, you can make a very precise prediction for the other. So if you can measure them both independently, then you're testing general relativity on cosmological scales. So it's really great. Very last 2 minutes, I'll just say something about LSST. So this is, as I said, the biggest project in astronomy. It's being built now on this mountaintop. Oh, I have the sound. Wow, I didn't even know that I had the sound. Anyways, it's being built there. You can see the camera is being built just down the hall from me at SLAC National Lab. And here's the telescope enclosure. So this is going to be able to detect objects about 100 times fainter than our current surveys at the same distance. So it's amazing. It's a 3.2 gigapixel camera that we're building. And it's going to take a picture of half the sky every 3 nights. Okay? So each piece of sky will be observed essentially every 3 nights, and we'll just go deeper and deeper over the entire part of the sky that this telescope can basically see. And so there's tons of science that we'll be able to do with this survey. But I've been most focused on the dark energy part of it, and so we will be able to do that weak gravitational lensing measurement very, very precisely, as well as several other kinds of measurements. So I'll finish there and just give you this overview of the universe. We actually are now able to measure things about this first tiny fraction of a second by looking both at the cosmic microwave background and then all the way to measuring how those density fluctuations grow and turn into galaxies today. And so we really have a lot to do, but I think we're almost guaranteed that the next 10 or 15 years are going to be interesting in this field. We're really just beginning this new generation of ways to map the sky. And at the heart of that is our ability to make predictions using these simulations and our understanding of how galaxies form within the dark matter distribution. There's really just going to be a dramatic increase in accuracy with this next set of surveys, and I hope you'll stay tuned for what we learn. Thanks.
Sorry if I missed it. I just wanted to come back to the question of why does dark matter not influence us on the solar system scale?
Yeah. Okay, so it comes back to that thing that I told you, that what happens with the gas is it sinks to the center of the dark matter halo. So that 85% number, that's on the scale of the whole universe. So now if all of the baryons become very concentrated, all of the normal matter becomes very concentrated, basically it makes up more of the total amount of mass where we have galaxies. So in the centers of galaxies where, just the fraction of dark matter is much smaller because that's where the normal matter has concentrated.
Why are they concentrating differently if both are responding to gravity in the same way?
Right, so they are both responding to gravity in exactly the same way, but one of them responds differently to it with electromagnetism. So the gas loses energy.
Oh, okay.
Right? It's because of the friction and that, right, so.
So the instruments that are being built around the world, the reason for doing that is it's just too expensive to put them in space, which would seem to be much more effective.
Right, so space is really expensive. If you can do something from the ground, you always should do it from the ground. And there are some things you can do well from the ground and some things you can't do well from the ground. So actually, I didn't mention it, but in my list of surveys, I actually had several future surveys that will be from space. So actually, a couple weeks ago, I was at a meeting that was focused on a telescope called WFIRST. And WFIRST will be able to do similar science from space. It's going to be beautiful in so many ways, but that won't launch until probably 2025 or so.
Is that the James Webb?
No, actually, James Webb is sooner. Okay. James Webb comes sooner. That's the next big thing to launch. And James Webb will do tons of really beautiful and interesting things, but it probably won't tell us a ton about. It's a very small field of view. So it will be wonderful for measuring the very early universe, for measuring the earliest galaxies that formed. It won't be very good at mapping large regions of the universe because it's just a tiny field of view.
Okay. Thank you, Risa.